Hello everyone, welcome to session number 3 of PH556 Astrophysics. Today we are going to be talking about opacity, which is a concept which we have touched upon in bits and pieces in different parts of different lectures, but now we are going to put it all together. So what is opacity? Suppose you have these two slabs of material over here where there's going to be light coming in from this side and an observer is situated here on this side. So what you have is when light is incident, suppose there are some photons incident on the first slab, some of these photons are going to get absorbed or scattered by this material over here, and a small fraction of that photons will come through. So what I've assumed here is that there were some say 8 photons incident here and about 4 of them came through. Now if we have another slab of exactly the same type, then how many of these photons are going to go through? So if you had 4 photons absorbed here, would you think that all 4 photons are going to get absorbed by this slab? Well, not exactly. What is going to happen is still you are going to get some photons coming through. In particular, in this case, what is happening is that if you had flux F that was incident on the first slab, then the flux that was transmitted through that slab is going to be F by 2, which is how we have chosen the properties of this slab. So about half the light that was incident went through, which means that the second slab is going to do the same thing, so that the flux that comes out from the second slab is now going to be F by 4 rather than being F by 2 in the case before. So in general, if you had n slabs of this type, then the flux that would come through is going to be F divided by 2 raised to n. Okay, so that's the general idea behind absorption, that absorption is a multiplicative process. It is not additive or subtractive, it is multiplicative. The fraction that is absorbed is what is determined by properties of that material. And this phenomena is used to define optical depth. So transmission is a negative exponential process. It is negative. You cannot get more light than you actually had incident on that slab. We are assuming that there is no generation of photons in this case. So the optical depth tau is defined such that the flux is proportional to e raised to minus tau, or actually equal F naught times e raised to minus tau. Okay, so the amount of light that goes through is given by F naught divided, so F I can say is equal to F naught e raised to minus tau. Okay, and this tau is called the optical depth of the medium. So now astronomers use more commonplace language to describe this. For example, you can say that an area or a medium is optically thin, or that it is optically thick. Optically thin, loosely speaking, refers to a region where absorption is in small amounts. Okay, so for example, suppose this box drawn here is a unit area box. Okay, so 1 square centimeter, and now let me add some spheres here that are going to block light that is trying to come through. Okay, so as I keep adding these spheres randomly, note that while I have a small number of spheres, the chance that these spheres overlap with each other is very, very small. Okay, so if the area of each sphere is AS and I have n spheres per unit projected area, then what's going to happen is that first these spheres won't overlap with each other, which means that each sphere is going to block about AS of the light coming through. So the total light that was coming through, a fraction AS times n, where n is the number of spheres, is what has been blocked. If I want to express this using optical depth, then the fraction of light which is transmitted is 1 minus n times AS, so that is e raised to minus tau. In other words, what we can say is that we can Taylor expand this to say that e raised to minus tau for small taus is roughly 1 minus tau, and for small optical depths this tau simply becomes equal to n times AS. Okay, so this is the optically thin regime. Loosely speaking, you can define optically thin as the regime in which tau is small enough such that this approximation applies. Okay, so this is simply a concept called column depth, and we'll come back to it later in 2 minutes. On the other hand, suppose I have what is called an optically thick case. Now suppose that these spheres which I am talking about, let's say that these spheres are actually atoms or something like that which are absorbing light, but now I have crammed a lot more of these atoms into the same box. Okay, so here you see a box which has a lot more of these spheres. Now if I add one sphere here, okay, let's look at this. The sphere was added in this part, okay, and that is hardly blocking any additional light as compared to what is being blocked. So my linear assumption where the fraction blocked was linearly proportional to the number of spheres that were doing the blocking is no longer valid. So this is called the optically thick regime. Loosely speaking, in optically thick regime, now second order and third order effects start mattering, so you start getting a lot more absorption. You have to start worrying about radiation that might not make it through at all, and other effects that can come in. For instance, if that much amount of energy is being absorbed, you have to worry about whether the absorbing cloud or whatever material you had itself can start getting heated up and start emitting more radiation. Okay, so this is the optically thin regime. Now let's come back to that column density concept that I talked about. Okay, so I have drawn the same box here, exactly the same box that you saw in the optically thin case, but now I am saying that you can assume that box is actually stretched in between. So this box is to be assumed really to be stretched out like this. Okay, and this view that you saw was on this side, whereas now you are seeing a view from this side over here. Alright, so what I can do is I have not yet, when we are looking at it from this perspective, I have not really defined where all of these particles were sitting. They could be stuff that is sitting near the source. This is called a circumstellar medium. If you are looking at a star, there could be a lot of gas and dust that is just present around the star itself. Or they could be distributed in between somewhere. It could be interstellar medium that is present between you and the stars. Similarly, medium that is present between galaxies is called the intergalactic medium. Okay, interstellar medium is sometimes abbreviated as ISM, interstellar medium, and you can have intergalactic medium as IGM. Or you could also have all of it completely near the observer. If you are in a crowded city, then the pollution and the amount of dust in air itself means that you might actually not be able to see the fainter stars. Okay, or you could have something that is, if you are looking at a high redshift source, then photons from that, there might not be a lot of IgM, intergalactic medium, blocking those photons. But when those photons come to our galaxy, then the dust and gas in our galaxy can start blocking out all of those photons, right? But here's the main point. All of these particles right now, they moved in a line where between the source and observer, you really did not have to worry about where they were, because as seen by the observer, they always remained in the same place. These photons these particles I had purposely in this rendering moved them in flat horizontal lines like this. So what we really are caring about is how many particles are there per unit area, how many absorbers are there per unit area. We don't care about their distribution in space in these first order effects, and that is why this brings up a term called column density. Okay, so if I have some species X, where X could be hydrogen atoms or dust particles or helium atoms or whatever, okay, then the column density Nx is given by the number density small nx, which is simply the number of atoms per cubic centimeter, multiplied by the distance. Okay, and that is the distance over which that material is spread out. So going back to the previous example, here what I would use is Nx would be the number density in this little area here. I would use this part, I would simply use this part as the distance, and I would ignore this entire part here, because I can assume that these particles so far are having uniform density small nx in this phase, but there is nothing here. Okay, so Going forward again, you have to take the number density in the relevant area, and you also have to take a relevant distance corresponding to that number density, and that will give you a column density in nx. Now distance is going to be measured in units of length. Number density is simply number per volume. So column density will have dimensions of per unit area. Now usually though in astrophysics we measure number densities in per cubic centimeters. Remember, we stick to CGS units, not SI, and distance itself is measured in parsecs. So column density is often expressed in parsecs per centimeter cube. Okay. Now what kind of sources of opacity can we have? So if you have free electrons, okay, then that gives you something called Thomson scattering. So imagine that I have hydrogen and I have ionized a few of those hydrogen atoms. So now I get free protons and free electrons. Now what is the size of an electron? That's a very tricky question. But for our purposes right now, what we can talk about is what is the effective cross-section area of an electron for absorbing a photon. So each electron from this perspective acts like a sphere whose cross-sectional area is, a sphere or any object whose cross-sectional area is 6.65 into 10 raised to minus 25 centimeters square. Okay, and this is called the Thomson scattering cross-section. So if you have some medium which is fully ionized, then the number of electrons that you would have depends on what is the atomic number of the species that was present and the number density of that species. So if I have say 100 hydrogen atoms per cubic centimeter, or if I want to take a projected area and I am saying that I have say 100 atoms per unit area per square centimeter, then, and if they are fully ionized, then that means I have 100 electrons. So Ne would be 100 electrons per square centimeter. On the other hand, if I have helium, if helium is fully ionized, then now 200 electrons will be present if I had 100 atoms of helium to begin with, right? So this head is the atomic number, and the column density that you need for electrons. If you are dominated by Thomson scattering, then you have to take free electrons which are not bound. So we are not talking about transitions between energy levels of atoms. You have to take the number of free electrons that were present. You calculate them using this formulation. If they are partially ionized, then you have to do more careful calculations, of course. And then per electron, this is now equivalent to the AS, the scattering cross section area that we talked about in some of the earlier slides, is 6.65 into 10 raised to minus 25. This is called the Thomson scattering cross section. Now that's electron scattering. What other sources of opacity can you think about? Okay, so I'm going to take a little bit of a pause here. We'll do old-fashioned classroom style counting. Let's assume that you had paused, thought about something, written down a few sources, and now let's go ahead and discuss these sources one by one. Okay, so the first source is something which I've alluded to even in this lecture, which is extinction by dust itself. And a great example of it is if you have seen pictures of the Milky Way, or if you have been lucky enough to actually see the Milky Way itself in the night sky in its glory, then you'll notice that the Milky Way appears like a band overall, but this band has some very bright patches, which is what you would expect. Now, Milky Way is pretty much a flat spherical galaxy. If you are in the middle of that galaxy, then it's going to appear like a band on the sky. These brightest regions, the very bright stars that you see, is what you would expect, because these are the places simply where there are more stars. If I'm looking up through this disk in regions like this, then I won't expect to see as many stars as before. But what you also see is there are these sudden regions here which are a lot darker. Okay, these places right next to these very large concentrations of stars are completely dark, and that is because there is a lot of dust which is present there, and that dust is absorbing all the light coming in. If we see infrared images of the Milky Way, and that's something that you need to do, just go look up Milky Way in infrared, then these dark areas don't appear anymore. What other sources of opacity can you think of? Okay, so atoms themselves have been contributing to opacity, of course. So you have high cross sections at specific wavelengths, and these wavelengths correspond to these transitions between energy levels of atoms. That also means that higher Z elements, which have more electrons, which have more electron levels which are possible, can absorb photons at a lot more wavelengths, and that is going to cause higher opacity. Okay, and there's something called line driven winds. So if you have these uh, very hot stars, there's a lot of intensity, a lot of light that is being emitted by those stars, and the outermost layers of those stars are seeing all of these photons coming in. Now if an atom absorbs that photon, then the atom is going to get the momentum of the photon. Remember, momentum has to be conserved, and that atom itself will now slowly start moving out. So if you have heavier elements present, now remember astronomy counting, we have hydrogen, helium and metals. So if an astronomer says metals, then you're talking about carbon, oxygen, nitrogen. Saying this in an organic chemistry class would give you a F grade, but in astronomy that's how we call it. So if you have any of these metals or heavier elements present in the outermost layers of these stars, then what happens is that these start absorbing a lot of these photons, and with every absorbed photon you are now getting a kick. Not only that, these particles now, as they are moving with higher velocities, will go and hit other atoms, which may be hydrogen atoms, who are not going to absorb those photons, and essentially the outermost layers start absorbing momentum from the photons that were coming out, which means that the outermost layers of this star will now start expanding and spreading outwards as stellar wind. So you may have heard about solar wind as a continuous plasma wind that is being blown away from the sun. But for hotter stars, heavier stars which are hotter, larger, these stars can emit these copious amounts of radiation, and if there are any heavier elements present there, then those actually help in driving significantly stronger stellar winds than seen in our sun. Lastly, let's look at spectral lines themselves, right? We have talked about opacity. So here's an example of various spectral absorption features. So you can see that this is how much radiation was being emitted by the star, and here I am seeing less radiation because I had opacity because of H gamma in this particular case, because of this particular transition. Now as you start going to higher and higher energies, you'll notice that the spacing between these lines is becoming smaller and smaller. Also, for reasons we have discussed in the previous class, these lines are not infinitely thin, they have a certain width. So as you come here, these lines actually start blending into each other. And what that means is now any photon in this region will be sitting on some line. So suddenly my continuum, which should have gone like this, has been reduced to this number. One particular point of interest here is this wavelength, which has been labeled as the Balmer break. Okay, at this point what happens is photons with wavelengths shorter than this are photons which have enough energy to ionize hydrogen from the second energy level onwards. That corresponds to about 3.4 eV. And at that point you don't need to have opacity because of all these line transitions. I can simply, if I have hydrogen which had electrons in the n equal to 2 level, then any of these photons will get absorbed by that because it will simply ionize. The extra energy of the photon will go as kinetic energy of the electron in this particular case. So what you see is that at this point suddenly there is a decrease in the radiation from the star, and this is called the Balmer break. And similarly there is a Lyman break corresponding to the Lyman series, and so on. So you can have these spectral breaks, which is where the opacity has significantly increased. Alright, so that's all for today. Before I go to references, let's remember we are all doing this online and remotely because there's a pandemic. Stay healthy, stay safe. Please play your role in dispelling any rumors. Please educate people about what are the right precautions that need to be taken. And hopefully this will be over soon and we will all be back on campus. With that note, here are the references for today. I will upload these on Moodle, of course, and we will see you in the next online lecture soon. Thanks. Bye.